All right, so what is a graph? Let's start with that, right? So a graph is basically pair of vertices and edges, right? And what are these edges? These edges are basically a relation on the Cartesian product V cross V, right? So you have some nodes, you name the nodes V1, let's say V2. I'm drawing a very simple graph and it's connected in this way. So what are my vertices? My set V is basically V1, V2, V3. And my edge set is basically, in this case, there's an edge from V1 to V2, and there's an edge from V2 to V3, right? So that's my edge set. Okay. Now, there are different types of graphs, so we'll get into that. So for instance, this particular set can be ordered or unordered, right? So we'll come to directed and undirected graphs. Okay, so there are lots of examples of graphs, right? If you want to, let's say, go from Housekas to Dholakua, okay? So how do you do that? Well, let's say you have two alternatives, right? A simplified case. So let's say this node depicts Housekas. So you have nodes which basically depict certain locations, right? So you want to go from Housekas to Dholakua, and you can either go via NH8, right? Go all the way to the highway and then go to Dholakua, or you can go via Ring Road, right? I'm just considering a simplified scenario over here, okay? Typically, what you would have on this is you would have some notion of, either the time taken or the distance on these edges, right? There would be some value associated with each edge. So such graphs are weighted graphs. So weighted graph is typically denoted as VEW, right? Where W is the weight function. So W is basically a function from E to R. So it could be distances, it could be time, and so on. If you are going from Housekas to Dholakua, you would typically want to, minimize the time that it takes to reach there or the distance that you travel to get there, right? So that would be a typical problem that you want to solve. That's basically the shortest path problem. Coming back to this edge set, right? So there are again two types of graphs. There are directed graphs and there are undirected graphs. Let's consider a graph corresponding to some social network, right? Maybe Facebook or something, or maybe LinkedIn, right? There, basically, what are the nodes? You could have each person as a node. The edges would correspond to some relation between them, right? Let's say this relation is a friend or a contact, right? Then that would be symmetric, right? If I'm your friend, you're my friend, or if I'm in your contact list, you're in my contact list, right? It's set up mutually. That kind of a relation would basically denote an undirected graph, right? So here, the edge set is unordered. And what is a directed graph? In a directed graph, let's say that the relation you're considering is something like, instead of friend and contact, the relationship we are considering is likes or follows. So now it's not necessary that, if A follows B, then B follows A, and so on, right? So that would be a directed graph where E is ordered, right? Another example could be that if you have one-way streets, right? Same example as what we spoke about in the traffic example, but you have one-way streets. Graphs can get much, much more complicated. You could have lots of attributes associated with the nodes and the edges, right? So a node could be a person, as we've seen in a lot of cases, like Facebook, LinkedIn, and so on. Now, there could be lots of attributes associated with a person, right? From the personal details to what food he likes and so on. And similarly with edges also, you can have lots of attributes. For instance, if you're considering a financial transaction, right? Let's say entity A transferred some money to entity B. So this would be a directed graph, right? Because transfer of money is in a particular direction. And what are the kind of attributes you would have with each edge? You would have things like, at what time the transfer was made, right? The amount of the transfer, the mode of transfer, right? Like, for instance, is it a bank transfer? Is it an IMPS, NEFT, and so on, right? So you could have lots of attributes associated with the edges as well. Okay. We'll basically be dealing with the simplified version. We are just going to consider a weighted graph, right? With one value associated with each edge. Okay. So what are some applications of graphs? So here is a particular link. So you can go and visit this link. So this is the Stanford Large Network Dataset Collection. It talks about different networks. There are problems around social networks. So it has lots of graphs over here. Then communication networks, right? Like email communications or citations, like which paper cited which other publication and so on, right? Collaborations, people collaborating on projects or GitHub collaborations and so on. The World Wide Web itself is a huge graph. Then Amazon networks, where you have relationships linking people with the products that they buy. So there are a lot of interesting problems to solve over there, like, which are the frequently bought products, or which is the community of people who buy certain products. Then road networks is again a very important problem, right? For instance, Google Maps is based on a road network. You want to find, the shortest paths or the shortest time path from some source to destination. So typically in such networks, the nodes represent the intersections or the points where intersections are there, and edges represent the roads that connect the intersections. Okay. And so on. So you can go through this list. There's a wide list. So, I mean, graphs are used in a lot of different settings, right? But let's have a quick look at some of this, right? The challenges are that these graphs are becoming really big. And it's no longer possible to run your algorithm sequentially, right, on a single node. So you have to parallelize the algorithms. Now, most people just assume that, there's going to be some software available which is going to parallelize it on multiple cores or on a distributed system, and I'm just going to use that, or map reduce and so on. But somebody has to get down to the level of actually parallelizing that code, right? And that's what we're going to learn, right? How do you parallelize these graph algorithms? Okay, so just some examples of very large graphs. So for instance, if you look at the Poxy online social network, right? So the number of edges is about 30 million. That's quite huge. A live journal, the number of edges is about 68 million. Okay, so these are very big graphs. There are lots of smaller graphs also. So there's a mix, right? And you can look at the different types of graphs that come about, right? From communication networks, citation networks. So again, citation networks, even if you look at US patent citations, right? That's about 16 million edges. That's really huge. Then, yeah, these are temporal networks, right? So these are graphs which change over a period of time. So processing over these becomes even more challenging, right? Because the graph is changing over time. So if you look at Stack Overflow, right, comments, questions, answers, it becomes really huge, right? So the number of static edges is 36 million, but if you consider temporality, then you're talking about 63 million edges. Okay, so that's really large again. Here's another one, right? Twitter and meme tracker, right? So these are of the order of 500 million. So that's about half a billion edges, right? So we are going to be talking about these kind of graphs, right? There are two kinds of challenges. One is that sometimes you just don't have enough memory even to store the graph, right? This is a particular problem if your graph has attributes with the nodes and the edges. So even storing these graphs becomes a challenge, right? And so typically what you do is you maintain a distributed in memory graph database. So again, you'll find tools to do that for you, but it's interesting to figure out how to do it yourself. Right? The other kind of challenge is compute, right? Not memory, but compute. So the processing that you have to do on the graph is so large, right? Maybe quadratic, that it's just too expensive to do on a single node, right? Even though the graph fits in the memory of a single node. So in order to do the processing, you basically parallelize it, distribute it, and so on, right? So you parallelize just to make sure that you get the results in a reasonable amount of time. All right. So that's what we are going to look at large graphs for, primarily from the compute perspective. Even if you look at it from the memory perspective, once you've distributed the graph because of memory or whatever, now you have to design new algorithms, right? You can't run your sequential algorithms. So you need your distributed or parallel algorithms in order to process the graphs. Okay. Let's just quickly discuss what are the different kind of problems we are going to be looking at. So what kind of different analytics are we going to be looking at? So there are problems around connectivity analysis, right? So what is the problem here? Essentially, like for instance, in social networks, so there are typically different communities which you can identify who basically are more closely linked together, talk to each other and so on. Community detection is a very common problem that people look at. Who is likely to switch from one community to another community, or what are the features associated with people who form a certain community, right? Even in the security space for terrorism and all that, the governments are very interested in that. So connectivity analysis is interesting. So one of the features that they use is strongly connected components. So what are strongly connected components? So I'm not going to describe all the problems over here. We'll go through it in the course, but let me just mention a few, right? Some basic ones. So in a directed graph, right, strongly connected components are those which basically you can reach every node from every other node in that component, right? So you may have an edge going across components, but you don't have an edge coming back from component one to component two, right? So if you look at component one and you look at all the nodes inside, you'll see that all the nodes are reachable from all other nodes, right? And similarly in component two, but across component one and two, there's no edge going back from component two to component one, because of which, you can't reach all the nodes in these two components. So that's why these exist as separate components. Okay. So we'll get informal definitions and so on, but I'm just trying to give you a high level idea of the kind of problems we'll deal with. Okay. Then there are problems around path analysis. So for instance, the most important problem is shortest paths, finding shortest paths from source to destinations. Google Maps, we've already talked about traffic networks, right? Road networks. So they would use shortest path algorithms to figure out your distance or the shortest distances from some source to destination, right? Then there are problems around centrality analysis, right? So here essentially the main question is how central or important is a node? How central is a node, right? And what do we mean by central? Well, there are different metrics. So we'll look at some of them. One of them is betweenness centrality. What is betweenness centrality? Let's say in a road network, right? You find the shortest path from every source to every destination. Now, what you want to know is that which is a node which has the maximum number of shortest paths going through it, right? Or well, how many shortest paths pass through a node, right? So now what do you expect? Nodes which have high betweenness centrality, right? They are going to be points of congestion. They are expected to be points of congestion, and you may want to do something about it, right? Similarly, in social networks, betweenness centrality typically refers to people who are kind of important in some context, right? Okay. So we will be looking at parallel algorithms, obviously, for these kind of problems. And as I said, right, there are two kinds of bottlenecks. Either the memory itself is a bottleneck, or the processing is a bottleneck. So typically there are two kinds of paradigms. The shared memory paradigm, right? You use things like OpenMP to parallelize your code. And then you have distributed memory paradigm or architectures. And you use something like MPI, right, in order to parallelize your code by using send receive messages. So one is a shared memory setting, the other is a distributed memory setting. We are not going to discuss accelerators in this course, so nothing about GPUs and so on. So there is work on GPUs, but one of the characteristics of graphs happens to be that they are sparse. Like for instance, the total number of edges is typically not quadratic in the number of nodes, right? Although I mean they can be quadratic in a clique and so on, but typically in most real world networks, the number of edges is linear in the number of nodes. Okay, so which means that the number of neighbors on an average that a node has is typically constant. So that means that it's a sparse graph. So what are the ways in which you can represent a graph, right? So one is an adjacency matrix, right? So what is an adjacency matrix? So you have V1, V2, V3, V4, right? V1, V2, V3, V4. So you have a row for every vertex and a column for every vertex. And the row V1 and column V2 has an entry 1. What that means is there is an edge from V1 to V2. Okay. In the case of undirected graphs, you ignore half the matrix. That's okay. Right? But you get the idea. So now the crux is that sure, you could store this as an adjacency matrix, but this is going to be really sparse, right? The number of entries that are non-zero is going to be very, very small, particularly when you're talking about huge graphs, right? They are not dense. Okay, there are a few nodes who are like really active, right? Like maybe Amitabh Bachchan on Twitter or Facebook or Virat Kohli for that matter. But the crux is that these are a few people. They may be having a high degree, but if you look at the average over all the nodes, right, the number of neighbors that a node has is typically going to be constant, very small. Okay. And now the point is that, most accelerators, like for instance, GPUs, work very well with dense matrices, right? GPUs work very well with dense matrices. And they're not very efficient when it comes to sparse matrices. Okay, obviously they do support it, but if you look at the computation bandwidths that they're able to achieve, it's far, far, far lower, right? So that's not just a problem with GPUs, that's also a problem with CPUs. The kind of flops that you achieve for graph algorithms or sparse matrix operations is much, much lower than what you achieve for dense. So that's been one problem in the world of computer architectures for a long time, that we are able to handle dense matrices and all very well. But when it comes to sparse matrices and graphs are almost analogous. Okay. Sparse matrices can be represented as graphs and graphs can be represented as sparse matrices. As a matter of fact, even for solving a lot of problems on graphs, right, people use sparse math libraries. Okay. But one of the problems has been that, when it comes to dense matrices, you can really make use of the computer architecture. You can make use of the cache and so on in a very effective way, because the access is not random, right? You pick up some block of data from a matrix, and there are lots of operations that you have to do on that, right? That's basically block matrix multiply. We will not get into that, but I'm just trying to give you an idea. But similar things are not known for sparse matrices or graphs, right? Because when you access an entry and you want to access the next entry, right, that may be very far off, right? It's more or less a random access. Okay. So that's why processing graphs is a challenge even on CPUs, right, in terms of compute bandwidth. But particularly when we talk about accelerators, it gets even worse. Okay. So moving data to the accelerator, then the accelerator trying to perform sparse operations, which it is not efficient at doing, and then returning the results back to the CPU, right? It just doesn't work. Okay. Again, people have done it for some artificial scenarios, but typically in real world use cases, it doesn't work. Okay, so adjacency matrix is not always the best way to store a graph. Again, as I said, right, it's very sparse. So you're wasting a lot of memory by using an adjacency matrix. So obviously the next best is the adjacency list, right? I'm sure you have looked at this, right? So basically you maintain a list for every vertex, and what you store in each list is the set of edges. So V2 and then maybe, sorry. So V2, you have an edge to V2 and V5 and so on, right? And so on. So you just store in a linked list or some suitable data structure, right? All the adjacencies. Okay, so that's the adjacency list. And mostly, yeah, we do use adjacency list instead of adjacency matrices, right? And what are the challenges we are going to look at? Well, let's say that you have this, so this is only 4 vertices, but typically, we've seen examples where you have millions of vertices. How do you distribute this across nodes, right? So you may say that, okay, let me give, 100,000, I have 10 nodes. So let me give 100,000 nodes to each processor. Now, how do you give these 100,000 nodes to each processor? You may just divide it by index, right? That the first 100,000 give it to processor number 1, the next 100,000 give it to processor number 2, and so on, right? That's one way of doing it. Another way of doing it is that maybe, like for instance, if you're doing road networks, you want to get all the nodes which are in the same locality together onto a single node, right? Do something like that, maybe east, west, north, south, center of the city, and so on, right? Divide it that way. Let's say you've divided the data. So now your vertex 1 up to vertex 100, let's say, are residing on one processor, and vertex 101 to vertex 200 are residing on another processor. Now let's take a simple operation, right? Even shortest path and all are more complicated, but let's take a breadth first search. What do you do in a breadth first search? Well, you pick up a vertex that is at the current level. So you maintain something called level. So again, we'll get into details of this, right? I'm just trying to motivate what is the typical problem you have. When you're doing breadth first search, you pick up a vertex at the current level and you want to basically mark all its neighbors to be at the next level, right? So if the current level is, let's say, level 5, you want to mark all the neighbors of V1 to be at level 6 if they already are not at a level lower than 5, right? If they have not already been reached in the BFS tree, you want to, if they have not been reached so far, you want to mark them to be at level 6. But what does this mean? The neighbors of V1 may not be on the same node, right? The neighbors of V1 may be on another node. So that then involves communication. And this communication, typically it's much more costly in comparison to the compute operations you're doing, right? So you can't follow the same models that you've been looking at in theory. So there's a huge difference between theory and practice. Okay. I mean, in theory, you would study PRAM models and so on. Even if you want to do a simple operation like a DQ operation, you have a queue and you want to take out the head of the queue, right? You would write an order log n algorithm to do that, right? In the PRAM model. That's not the way you work in practice, right? In practice, it's much, much more efficient to just do an atomic operation. We'll be looking at algorithms. It's not meant to be a theoretical algorithms course. It's meant to be more a practical algorithms course, right? More coming from the parallel side of things. So we'll be approaching it more from practical point of view. Okay, so yeah, so the communication is much more costly in comparison to the compute, and therefore, you've got to design algorithms where the communication is minimized, right? So again, we'll look at those kind of things.